Yeah, wonderful. Good morning, everyone. It's a pleasure to be here. Thanks for inviting me to this exciting summit. So in my presentation, I would like to talk about the what, why, and how of haptic communication. Haptic communication as a technology that comes into the picture when we try to realize tactile internet applications where the human is in the loop and where we want to allow the human to remotely and physically interact with objects in the distance. So I'll talk about what is haptic communication, at least from my perspective. I'll talk about why it's interesting to look at this also from a scientific academic point of view, because you're going to see there's some things that we need to do differently from what has been done in audio-visual communication, for instance, in the past. And I'll also show some examples on how to realize it. Now, in order to motivate it, let's first look at today's telepresence systems. I guess we're all familiar with that. Think of a video conferencing system, for example. And in these systems today, we mainly have audio-visual information flowing between the different parties in order to allow remote interaction. Now, with the very efficient codecs we have, the broadband networks, and the high-fidelity input and output devices, so capturing and display devices, these systems at least partially fulfill the promise of immersing a person into a remote environment and to generate a certain feeling of presence. Now, one interesting thing to note here is that although the actual conversational service that we enable here at the application layer is bidirectional, because you communicate, the underlying audiovisual communication really is 2 times unidirectional. You have audio and video being recorded on either side, you compress it, you packetize it, you transmit it, and you display it on the other side. And in fact, we do quite some effort in separating the forward and backward channel. Just think of echo cancellation, for instance, as one example. Now, although these at least give us some feeling of presence in a remote environment, I would argue true immersion into a remote environment is only possible if you're able to physically interact with the objects and the persons in this distant space. Now, this becomes possible if we add a third modality, the haptic modality, and then this picture is changing. Now we have an operator here on the left-hand side who's commanding a robotic system at the remote side. That robotic system is a laser pointer here. That robotic system is equipped with sensors and actuators, and as you get in contact with the environment, these sensors gonna sense the interaction parameters, feed them back to the operator, where it's then displayed through an appropriate human system interface. Now, the things to note, or the differences compared to what we've seen on the previous slides, is now there's 2 local control loops. One here at the operator and one there at the teleoperator, and the communication network in between connects these 2 local control loops into a global control loop. And I guess we all know from our basic course on control theory, if there's latency in this global control loop, very quickly things can become unstable and in some situations even dangerous. Now, you could argue, well, do we really need this haptic feedback here from the remote side? Why don't we just command the robotic system and observe what's happening rather than being really coupled into this interaction? There have been numerous studies that showed that when an operator has to complete a certain task, this haptic feedback, in fact, improves the task performance. And the scenarios where this has been studied, they range from telesurgery all the way to teleoperation in space, for instance. Now, the other thing to note here is that now the communication is truly bidirectional, right? So it's not 2 unidirectional communication chains we have here. But now, whatever command you put here on the forward link, through the coupling of your robotic system with the environment, reflects immediately back to your side here and influences how you react to that. So you're really in the loop here. So that makes a fundamental difference in terms of how we have to deal with these systems. So when we talk about haptics in general, we need to distinguish between 2 main perceptual concepts that we as humans have. One is the kinesthetic perception. We had it briefly in one of the presentations already yesterday. And this really relates to the perception of your pose, of your body parts, your limbs, your joints, and the forces and torques that are exerted on your body. Right? And we basically perceive this through our bones, muscles, and tendons in our body. On the other side, complementary to that, we have the sense of touch in our fingers, for instance, in the skin. And this is perceived by different types of mechanoreceptors that we have in our skin. And the two things, of course, for us as humans always coincide. If I lift this object here, I feel its weight. That's kinesthetic perception. But I also feel it's plastic, it's rigid, it is smooth. And that's tactile perception on the other side. So they always come together. Now, in technical system as of today, they're separate, right? And that's why also I'll look at these two aspects when we try to do it in terms of haptic communication separately here. So this is a typical kinesthetic teleoperation system. You have, in this case, a 7 degree of freedom haptic interface. It can sense 3 positions, 3 orientations. It has a gripper where it can sense the opening. It can also display 3 forces, 3 torques, and also force feedback on the gripper. And then the human operator commands basically a robotic system on the other side, which follows these commands, and then the sensors in that system measure the contact forces and torques and reflect them back here, and you display them on this side. No? And as I said, it's very critical here in terms of delay, so there's a closed loop communication. In order to make this a good experience and to be able to feel, for instance, stiff or rigid surfaces, typically you need between 1,000 to 4,000 updates being exchanged in both directions here in this system. Yeah? Depends a little bit on the compliance of the system if you operate at 1,000 or at 4,000, but for the high quality systems, people sometimes even go up to this number here. Now, as delay is very critical, typically what you do is you take every sensor reading and you immediately send it to the other side. So you put it in a packet and you send it, which means we deal with packet rates flowing both directions here in the order of 1,000 to 4,000 packets per second. We have very strict delay constraints. If we want to operate this without special control measures, we typically need to stay far below 10 milliseconds in order to have a stable interaction with this remote environment. Although we can do that, right, there's still lack of realism. And the reason for that is these systems here, they're mechanical systems, and they have some limitations on their own. Yeah? So they are compliant, for instance. And when we tap with our finger here on a hard surface, it's not only that we feel the contact, but we also feel the vibrations that are introduced in our finger, which kind of, again, make this joint experience of kinesthetic and tactile feedback. So when we run these systems here, typically what we have is a certain lack of realism because we are missing these high-frequency components in the signals, which simply cannot be displayed through the devices we have on this side. And that's why we typically try to complement this then with a tactile feedback independently, but overlaid at the end. And that's a typical setup where in addition to the robotic device, now you see teleoperator and operator is actually the same device. Here, for instance, we put another accelerometer on the tool that is in contact with the surface. We record the acceleration signal, we transmit it to the other side and display it on a tactile actuator, in this case a voice coil device. Right? Now the interesting thing to note here is this is not closed loop, this is open loop. Right? Now here you record, and with very relaxed delay constraints you transmit this to the other side and display it in addition overlaid to the kinesthetic feedback. Yeah? So here we have relaxed delay constraints, and we achieve improved realism as we put both together. Now, since these two things are different, one is closed loop, one is open loop, they need to be handled differently. So I'll go through the two parts separately in the following. Okay, so what is the challenge here when we do this kinesthetic teleoperation? It's the same scenario here, basically, now in a manufacturing scenario, maybe where an operator is remotely controlling some maintenance robot. And if we want to avoid that we really have to exchange these 1,000 to 4,000 packets per second, we do what we always did in compression of modalities, we do perceptual coding. Yeah, we exploit that the humans cannot perceive every subtle detail of information, and what cannot be perceived does not have to be transmitted. But here the situation is different. We're not interested in reducing the raw data. We're interested in reducing the number of packets we have to send on average, because this is really the what puts a burden here on the network. And if we do that, we can exploit that humans cannot perceive every single change in sensor readings here. We end up with a transmission which is very irregular. If you're in free space with your remote teleoperator, there's no feedback to return to the user. The moment you get in contact with the surface, you need a series of very quick updates, which means you have a very bursty traffic that you experience. And then for a short time, you might need to do the 1,000 to 4,000 updates per second, but only for a bursty short situation. Yeah? So this really leads to an event-based sampling and communication that we have to put on top of the network. And of course, it would be great if the network would give us a mechanism to actually realize that. Now, this was below 10 milliseconds. And I guess we're all aware of the fact if we want to do this across continents, this sheer limitation, physical limitation, speed of light will quickly bring us above that. Now, when we do this with increasing delay, of course, we can still operate. But what we need to do is we basically need to damp the system. So we put stabilizing control on top of this, and this typically means that we try to damp the system. At the same time as we do that, of course, we lose in transparency, which is basically related to the quality of experience for the user, which for instance means if I remotely tap on this surface here, it's no longer hard. It's going to feel soft to me because the system itself introduces some damping. Now, there's a number of architectures that have been proposed to stabilize these systems even in the presence of a couple of 100 milliseconds delay. And I won't go into too much detail. I just want to pick out two different, let's say, lines of approaches here. One is to make the communication system in between passive, which basically assumes that the operator HMI interaction is passive. We can pacify the interaction of the robot with the environment. And then the only thing we need to make the overall system passive is to pacify the communication. So we need to check if by means of the delayed communication, there's energy generated in the system. And if this is the case, these passivity-based approaches, they dissipate this energy, which leads to a loss of transparency. For instance, sudden force, erratic force peaks that you experience in this system. An alternative way of doing it is, so here we have maybe up to 100 milliseconds, a good experience. Another way is to basically cut the loop, so go from the global control loop here that we have, cut it by taking a measurement of the environment on the remote side and having a model representation of this environment locally available here, and then do the whole interaction locally. Now the haptic rendering is done in a virtual environment which reflects what the environment is at the remote site. This way there's stability by guarantee, right? Because there's no delay here in your local haptic loop, so you can interact with this model. The challenge, of course, is this model always just going to be an approximation of the real environment on the other side, so you constantly need to update, right? If you move into a different part of the scene, you need to update that model. If you have an estimate of the geometry, it's going to be slightly wrong. You need to update as you move closer and closer and so on and so forth. So now the challenge is really in determining how this model, how the environment looks like, and to represent it in a local model here. But with this, we can even go higher typically in terms of the delay we can cope with. 200 milliseconds is definitely possible here. Okay, but now the model errors and the updates lead again to reduced transparency. It's always the same game. You go to higher delays, you lose in transparency. Okay, I'll skip that one here, but because the bottom line is, if I have a certain metric that determines how satisfied the user will be with this particular scenario, and I look at the end-to-end delay that is in the system, there might be different ways of controlling the system, right? So for instance, at low delay, this one I didn't talk about might be the one that leads to the best user experience. But then as we move in medium range delay here, let's say 80 milliseconds or so, a different control scheme will give a better experience. And then as we go to very large delay, maybe this model mediated teleoperation gives us the best experience. So ideally, we want to operate on this envelope curve here, which means depending on the situation, we might actually have to switch between different control and communication schemes. So bottom line really is we need to do a joint optimization of the network, the control, and all is driven by what objective we want to achieve, quality of experience, or sometimes just the task performance, because you can perform a task even if you feel some artifacts, let's say, in the tail operation. Okay, so this was the kinesthetic part. So I'll move then on to the tactile part. And this one I would say is easier. Easier in some sense, because when you look at this tactile information, this high frequency vibrations that you need to capture and display, shows very strong similarity to speech signals. So this is a standard speech codec. And the only thing we really need to do is we need to change the model of human, now tactile perception. So we take out the speech or acoustic model that is in there and replace it by a tactile perception model, and then we can operate this at very low bitrate, for instance. But remember, it's open loop. We can capture the data, we can process it, and this, of course, is what is done here. We need to work on a certain block of samples, and then we compress it, transmit it, and display it on the other side. Now, in the last 1 or 2 years, I would say very interesting things are happening in this area because there's new display devices that allow you to display this tactile feedback. So this, for instance, the T-Pad phone, which allows you to locally modulate the friction between your finger and the glass plate of your touchscreen. And by this, of course, as you slide your finger over the surface, although the surface is flat, with this modulation of friction, you get the feeling of bumps and a certain texture on the surface. I actually have a device with me if you want to play with that in the break later. Now, other approaches like the Tesla Touch, for instance, from Walt Disney Research, they just invert the concept of a touch display. Right? They put voltages now on the connections here to the display, and then they exploit the electro-vibration mechanism. As you slide over the surface, there's charge in the tip of your finger that accumulates depending on the voltage you put on the device. And then you can modulate the force that you feel by this, and again, modulate the friction across the surface. Or there's more classical devices like the Haptuator here is a piezoelectric element where you can control the frequency of vibration and the amplitude of vibration and just attach this, for instance, to your finger or build it in a device and put your finger on top of that. Now, the T-Pad guys here, they put out a challenge end of last year, and asked academics and other people who wanted to participate, what can we do with this? What kind of applications can we realize? And I want to show you one that we put into this context here, and this is what we call a remote texture render. So there's 2 scenarios that you're going to see, and the first one is just experiencing different materials, and this could be an e-commerce scenario, right? You shop in the internet, you see this sofa, you see it, but you also want to know how does it feel like, because before you buy it, you want to have an idea about the look and feel of it. So in this T-Pad application that we have here, you can load now different textures, and this is from a database that we have recorded, and then basically experience the feel of that surface on your smartphone as you interact with this. Here you can also put 2 side by side and then basically distinguish between different ones or search even for materials or surface properties that are similar to the one but maybe a little more comfortable, little colder, whatever you're interested in. So this is pre-recorded textures that you could make available. But even more interesting is maybe to go to the point where we actually communicate it, where we allow you to remotely experience any surface. And this is then what we have in the second scenario. Imagine your spouse is in the furniture store, sees that sofa, and sends you a picture. I guess immediately you're going to ask back, how does it feel? So the idea here is that you could take a picture of the surface, so then you see how it looks like. But then also you want to capture the characteristics of the material of the surface. And we do this here after taking a picture by simply relying on the accelerometers which are built in your mobile device. We have a small steel tooltip here, and then as you scratch with that over the surface, we record these signals, we extract the texture model of it, send it to the other side, and then display it again to the user. Yeah, so here you can then touch the world in your hand. Okay, now it's not the pure signals that we communicate, right? So from the data we capture, we even use the microphone for that. We basically extract the main dimensions of tactile perception, which have to do with roughness, with friction, with it's mainly micro, macro roughness and friction, generate a texture model which can then be standardized and displayed on any device that supports that. Good, so this brings me to some conclusions here. I hope I could show you that haptic communication is something that comes into the picture when we want to remotely interact with objects. There's some fundamental difference between these two components, the kinesthetic part and the tactile part. One requires closed loop communication, which is of course more demanding. The other is open loop, is more like the traditional audio-visual communication that we have. In particular for the kinesthetic data, we've seen it's fundamentally different from audio-video. There, we always want to compress the data as much as possible. Here, we want to reduce the number of updates we send. Actually, the payload is relatively small in these scenarios. I also showed you that if we do smart control schemes on top of that, we can even operate at delays of 100 or 200 milliseconds. So the 1 millisecond, which is sometimes set for tactile internet, of course also only applies for very, very dynamic scenes you interact with. And I would say if the scene is so dynamic that you need a delay of 1 millisecond, then it's better to let a machine do that interaction locally and just steer. And this was actually Jens' example yesterday with flying the quadrocopter. Of course, you don't want to compensate for all the vibrations and the wind. You want the local control algorithm to take care of that and just steer that quadrocopter to a certain point and do some maneuvers. But you don't want to do the subtle control manually from remote. We've also seen there's different control approaches for different delay ranges, so we might have to switch between different schemes as we encounter different end-to-end delays. And in the second part, I showed you that these tactile feedbacks that are emerging now open new types of opportunities we can look at. I have a few to-do things in order to enable that. That's now mainly about the how. And I guess the most important one is the first bullet here. We need to standardize parts of this. We need to standardize the protocols, how to do the handshaking, how to connect to remote devices with these capabilities. We have to define the signal formats, and we have to standardize the codecs for that, right? So we become interoperable in that sense. We also need to jointly optimize communication and control. I guess you have seen that. There's of course a lot of work left to be done in the haptic input-output devices. We want to do this bimanually. Right? We want to do kinesthetic interaction with both hands, and these devices are not really there today. For the tactile interaction, we want to do this with more than one finger, because if you go on the T-pad, for instance, today, and you put 2 fingers, you feel the same thing in both fingers, because there's just one type of friction at the time that you can display. And of course, you want to have multi-finger touch, for instance, there. This one I'm particularly concerned about because everything we do in this space today requires expensive and costly subjective tests. We invite 20 students to come in the lab and we test then algorithm A or system A against system B. And it would accelerate the progress in this area tremendously if we had objective quality metrics that would tell us how a user would evaluate that particular application at this time. And then, of course, we will need to bring it to a certain use cases and application and show that it leads to a real advantage. With this, I conclude my presentation. Thank you for your attention.
Thank you very much for such an inspiring, interesting talk. There are questions.
Have you investigated any issues with teleoperators syncing touch to audio and video? And in fact, are there issues with that? Because it seems like if you have all these different codecs running, then you in fact may get the different sensory information at different times.
Yes, definitely. Yeah, so there's a very simple, let's say, rule of thumb, and this is touch goes first. Yeah? When you get in contact with an environment, and if you see the contact before you feel it, it's disturbing. If you feel it before you see it, it's okay. You can easily adapt to that. And then, of course, there's psychophysical studies that show if the asynchrony between these different modalities is, let's say, below 40, 50 milliseconds, it's even hard for you to distinguish. But once it goes beyond that, very quickly it's difficult for the user to associate events. Because in the interaction, there's many things happening, and once you go above a certain delay difference in the 2 or 3 modalities, suddenly the touch event is no longer associated to the correct visual event. And then, of course, the whole thing becomes extremely disturbing. So synchronization is very important. I showed you this model-mediated approach where you have a local model of the environment and you interact locally. So here your haptic feedback comes in 1 millisecond, I would say. But the video that you receive from the other side could be 100 milliseconds behind. And there is exactly the situation where you run into trouble. But I would say from a psychophysics point of view, is well studied. So we know the limits where we need to be in, but it's not reflected in today's implementations of that so far.
Thanks. This is great stuff. Just one thing that came to my mind when I was hearing you talking, pseudo-haptics. And if there is some theories on pseudo-haptics that could be used when we design, communication system for haptics, or not?
I think I missed your first part.
Pseudo-haptics, it's a kind of this medical phenomena that you can replicate haptics and without really.
Yes. Yes, more I would say on the display side. So for instance, there's this very famous funneling effect. You put a vibration element here at the bottom of your arm. You put one here, and if you can control the amplitude of those 2 vibration elements independently, you can generate a sensation where your touch sensation actually moves up the arm. And you can do this basically continuously. There's other work that, for instance, directly goes on your nerves and basically replicates the signal that you would normally send to the brain when you lift some object. So if they, blindfold you, they can actually make you feel lifting a 10-kilogram weight, but you have nothing in your hand. Yeah? So I think these 2 things need to go hand in hand. We need to understand how we can trick, let's say, the human perception in that sense. How can we make sensations that are believable and consistent with what you expect without putting, huge hardware there, because this is what you end up with if you try to capture everything and make it on the signal level. You have a very big mechanical device, let's say. Yeah.
Okay, Jens, the mic. Yeah.
Yeah, I thought this concept of model-mediated kinesthetics is very interesting, and I think at the very far end, it's basically autonomy, as you mentioned the quadrocopter example. That then you actually give only some steer parameters, and then the thing goes off by itself.
Right.
And in that case, the autopilot of a plane is sort of the model is sort of clear. It knows it's a one type. It's one application, and you can tailor-made your model for that. But how difficult is it to can you see some other situation? How difficult is it to make this model that you need for model-mediated interaction?
Yeah, it's definitely the challenge there. And I can give you some examples. The whole thing started with very simple models, just having a planar local approximation of your environment. And as you approach, and let's say you just need a simple distance measurement, then locally you can have this plane virtually being at the point where you expect to get in contact, and then you render this contact locally. It's nicely stable. Now, if I would do this with already a little more complicated scenario, of course I would need to scan this surface in order to get the geometry right. So we do this with a Kinect, right? We have a Kinect on our manipulator, and we basically have a 3D model of the sea in a point cloud before we even touch it. But the thing then is we have the geometry, but we don't know the stiffness, right? Because the stiffness you can only determine once you really get in contact with it. So maybe you start with a very rigid surface, but then once the teleoperator gets in contact, of course you can measure the penetration and the stiffness parameters of that surface, and then this is the model update that you need to send to the other side. And then of course the user will from a hard surface now feel, okay, this is actually a membrane, is maybe soft. And I guess some sensors might actually allow you to do that even without touching, to infer at least some first idea, is this a rigid or more soft surface? Think of radar or whatever, trying to penetrate and being reflected. or maybe new sensor concepts are needed there. But this generating an accurate model and updating it continuously, that's the critical challenge here.
So what you're saying is that you basically can do the modeling on the fly. I mean,
We do it on the fly, yes.
Okay, so
yes.
it doesn't need to be any. I mean, the airplane it's a sort of pre-installed model now. The
Yes.
autopilot is a
Yes.
pre-installed model, you say, of how the
Yes.
plane dynamics.
Right.
But here you do it on the fly.
Yes. There's certain scenarios where you can have the complete model available. Like our colleagues at the DLR, for instance, they have a manipulator being installed on the International Space Station. And of course, they know the geometry, the dynamics, and everything of that. So when they remotely control it, they basically have this CAD type of representation locally where they interact, and they just need to occasionally synchronize. But if you go into an unstructured, arbitrary environment, I would say online modeling is what you really need to do. Yeah.
Do you have any idea how you actually reach objective quality metrics? I mean, is it just the number of people you put into a test, or you have to cover different age groups? Because the feeling, I think, is quite subjective. So how you actually get there?
Yeah. So in the subjective test, we typically try to go across a huge aged population. We focus more on students because they're easier to get in, but we also ask the layman on the street. Typically, we have about half people experience with haptic interfaces, and we take in half people, 50% of people that never had a device like this. And then, of course, you do the statistics, you remove outliers, etc. The objective metric is so difficult here because the human is in the loop, right? So you need to also have a dynamic model of the human that you put into that. And that's, of course, different from audio and video, where you just analyze the signal, have a perceptual model of how humans would perceive that, and come up with a number that tells you how good that signal is.
If there are no questions anymore, let's thank the speaker again.
Thank you.
And